Here we have a pre-calculus problem. Okay, let's go to the question. Prove that log 2 positive 16 times log 16 over 15 positive 12 times log 25 over 24 positive 7 times log 81 over 80 equals to 1. Okay, here we have to prove that the value of this logarithmic expression is equal to 1 that we have on the right side. Okay, now let me take this expression and evaluate it, and we have to prove its value is 1. Okay, now let me write the expression we have on the left side as it is. That is log 2 positive 16 times log 16 over 15 positive 12 times log 25 over 24 positive 7 times log 81 over 80. Okay, here let me consider the power rule of logarithm, that is n times log base a of m. Okay, here we have a logarithm and it is multiplied by some value n. Whenever a logarithm is multiplied by some value, what we can do is we can take this value n as the exponent for the argument we have over here. That is, we can write this one as log base a of m to the nth power. This is called a power rule of logarithm. Now I'm going to apply this power rule in this logarithm, in this one, because all these three logarithms are multiplied by some value. Here it's 16 is multiplied, here 12, and here 7. Okay, let me continue over here. Okay, and also let me write this first term as it is. That is a log 2 positive. Now we can write this 16 as an exponent for this argument we have over here. Then I'm getting a log of 16 over 15 whole to the power of 16 positive. Now let me take this 12 as an exponent for this argument. Then I'm getting log 25 over 24 whole to the power of 12 positive. Let me take this 7 as an exponent for this argument. Then I'm getting log 81 over 80 whole to the power of 7. Okay, now let me consider the product rule of logarithm. That is, let me add two logarithms with the same base. That is log base a of m positive log base a of n. Okay, here I add two logarithms with the same base a. Whenever I add two or more logarithms with the same base, what I can do is I can take logarithm once with whatever base I have for the logarithms, and I have to multiply the two arguments m and n. Then I'm getting log base a of mn. So this is the result of addition of two logarithms over here with the same base. So this rule can be extended even for more than two logarithms with the same base. Okay, so here let's consider the expression. So here we have addition of four logarithms. What is the base of each of these four logarithms? Actually, the base is not mentioned. Okay, whenever the base of a logarithm is not mentioned, we can assume it's a common logarithm, and for a common logarithm, the base is 10. That is, we can assume each of the four logarithms over here as common logarithm. Then the base for this one is 10, the base for this one is 10, and the same base we have for all the logarithms, that is 10. We don't have to mention, we have to assume the base for each of these four logarithms is 10. So we add four logarithms with the same base. Now what we can do is we can take logarithm once and we have to multiply the arguments as I explained over here in the product rule of logarithms. Okay, now let me multiply the arguments. Then I'm getting 2 times 16 over 15 whole to the power of 16 times 25 over 24 whole to the power of 12 times 81 over 80 whole to the power of 7. Okay, now I'm going to write this 16, 15, 25, 24, 81, 80 as a product of the prime factors. Okay, first let me take this number 16 and let me write 16 as a product of this prime factors. That is, we know that 16 is a power of 2, so it can be written as 2 to the 4th power. So the value of 2 to the 4th power is 16. That is, this 2 to the 4th power is a product of prime factors of 16. Now let me take this 15. So this 15 can be written as 3 times 5. Okay, here both 3 and 5 are prime numbers. So 3 times 5 is a product of the prime factors of 15. Okay, now let me take this 25. So 25 can be written as 5 square. And let's take 24. And this 24 can be written as 8 times 3. And we can write this 8 as 2 to the 3rd power times 3. Okay, here we have a prime number, here we have a prime number. So it's a product of prime factors of 24. And now let me take 81. So this one. So we know that 81 is a power of 3. That is, it can be written as 3 to the 4th power. And now let me take this 80. That is, 80 can be written as 16 times 5. And we know that 5 is a prime number. And 16 can be written as 2 to the 4th power. That is 2 to the 4th power times 5. Okay, now I have written these numbers 16, 15, 25, 24, 81, 80 as a product of the prime factors. Okay, now what we can do is, let me write the stuff over here. Log of, actually this is a prime number, we can keep it as it is. And now we can replace the 16 by 2 to the fourth power, that is 2 to the fourth power, and this 15 can be replaced by the product of their prime factors, that is 3 times 5. Let me write it. So now we can take a whole power 16, and we can write this 25 as 5 square, and we can write this 24 as 2 to the third power times 3. Let me write it over here, whole to the power of 12. And now we can write this 81 as 3 to the fourth power, and this 80 as 2 to the fourth power times 5. Let me write it over here, whole to the power of 7. Okay, now log 2 times okay, here we have an exponent 16 for this fraction. Whenever we have an exponent for a fraction, what we can do is we can take this exponent separately for numerator and denominator. When I do so, I am getting 2 to the fourth power whole to the power of 16 divided by 3 times 5 whole to the power of 16. The same thing here, we have an exponent for this fraction. Now we can take this 12 as an exponent for numerator and denominator. Then I'm getting 5 square whole to the power of 12 divided by 2 to the third power times 3 whole to the power of 12. And the same thing we can do over here, that is 3 to the fourth power whole to the power of 7 divided by 2 to the fourth power times 5 whole to the power of 7. Okay, now let me erase some stuff and continue the problem. Here we have the last step of our previous work. Okay, let's do further simplification. That is log of 2 times. Okay, here we have the base 2 and we have the exponent 4, and for this complete stuff we have the exponent 16. Okay, now whenever we have two exponents like this, what we can do is we can multiply these two exponents using the power of a power rule in exponents. Okay, then we get 2 to the power of 4 times 16 is 64. Okay, here we have product of two numbers and we have the exponent 16 in common. Whenever we have product of two numbers and there is a common exponent, what we can do is we can take this exponent 16 separately for this 3 and 5 and multiply the results. This is the power of a product rule in exponents. That is 3 to the power of 16 times 5 to the power of 16. Okay, here we can multiply these two exponents using the power of a power rule in exponents. Then we get 5 to the power of 24 divided by, and here we can take this exponent 12 for this one and this one separately and multiply the results. Then I'm getting 2 to the third power whole to the power of 12 times 3 to the power of 12 times 3 to the power of, when we multiply 4 and 7, I'm getting 28 divided by, so here we can take this exponent 7 for this one and multiply the results. Then I'm getting 2 to the fourth power whole to the power of 7 times 5 to the power of 7. Okay, now let's do some more simplification. Log of 2 times 2 to the power of 64 divided by 3 to the power of 16 times 5 to the power of 16 times 5 to the power of 24. Okay, here we can multiply these two exponents. Then I'm getting 2 to the power of 36, that is 3 times 12 times 3 to the power of 12 times 3 to the power of 28 divided by 2 to the power of 4 times 7 is 28 times 5 to the power of 7. Okay, let me continue over here. Okay, log of, now we can multiply the values in numerator. Okay, when it consider the values in numerator for this one and this one, we have the same base. Actually, we can consider this one as 2 to the first power. So here we multiply two powers with the same base. Whenever we multiply two powers with the same base, what we can do is we can take the base ones and we have to add the exponents. When I add 1 and 64, I'm getting 65, and we can write these two powers, this one and this one, as it is. That is times 5 to the power of 24 times 3 to the power of 28. Okay, now let me multiply the values we have in denominator. Okay, here we have two powers with the same base 2. So the same thing, that is we can take the base ones and we have to add the exponents. When I add 36 and 28, I am getting 64. Okay, here we multiply these two powers with the same base 3. So we can take the base ones, that is 3 to the power of, we can add the exponents. That is, when I add 16 and 12, I am getting 28. Okay, here we multiply two powers with the same base 5. So we can take the base ones and we have to add the exponents 16 and 7. When I add 16 and 7, I am getting 23. Okay, here we can cancel this 3 to the 28th power and 3 to the 28th power over here. We get log of 2 to the power of 65 times 5 to the power of 24 divided by 2 to the power of 64 times 5 to the power of 23. Okay, here log of, we divide two powers with the same base. Whenever we divide two powers with the same base, what we can do is we can take the base ones and we have to subtract the exponents using the quotient rule of exponents. That is, when I subtract the exponents, I'm getting 65, negative 64. The same thing we have over here. We divide two powers with the same base 5. So we can take the base 5 once and we have to subtract the exponents 24, negative 23. Okay, here we have log of 2 to the power of, okay, when I subtract 64 from 65, I'm just getting 1. That is, we get 2 to the first power. 2 to the first power is just 2. Okay, here 5 to the power of 24, negative 23 is just 1. That is, we get 5 to the first power, it's just 5. Okay, then we get, okay, let me continue over here. We get log of 2 times 5 is just 10. Okay, as we have discussed earlier, whenever there is no base for a logarithm, we have to assume it's a common logarithm, and we have to assume the base is 10. So for each of the logarithm in the given expression, in the given equation, there is no base, so we have assumed it's a common logarithm, so it has base 10. So the same base 10 we can consider over here. Okay, now in this logarithm, the argument is 10, the base is 10. In any logarithm, if the argument and base are equal, then the value of such logarithm is 1. Okay, I took the expression we have on the left side of the equation, and I got the value of this expression, and I got its value, it's 1. So that exactly we have on the right side of the given equation. So now I have proved the given statement we have over here.